Okay, as I talked about during class yesterday, um, because there are different people in class with the ACT day happening for juniors, like I told you guys in class on Monday, I'm going to do this recording for you to watch this on your own time. And of course, like I said, the second day that you're in class, you'll be taking the test. I've highlighted in orange problems that are very similar to ones that you're going to see on your test. So please look at the rest of them, but pay very close attention to those. Okay, all the ones that are not um, a lot like problems that are on your test, I've already solved and answered, and I'll be scrolling through those if you need to stop and pause to check your work or to look through that problem. Feel free to do that on your own time. But anyways, the ones that are in orange are a lot like the problems that you're going to see on your test. Okay, so let's start off with number one. Again, you're supposed to determine whether it's growth or decay. So remember, it's all about the base of that exponent. On number one, the base is 2/3. That's clearly less than 1. That's why it's decay. But if you look at number two, the base of that exponent is 6/5. Now again, don't focus on the fact that it's a fraction. Focus on the fact that the value of 6/5 is 1.2, which is definitely greater than 1. And therefore, this one is going to represent exponential growth. Okay, so make sure you're aware of that. All right, we're going to go to number three as well. I'm going to, since this one is very much like one that you're going to see on your test, I'm going to type it in here into the calculator with you, and then go over all of the specific things that are going to be important for you. So we have 3 to the x plus 1. And then, of course, we're going to scroll down and put the minus 6. So when I graph this thing, hopefully what you notice is this thing shifted down. Look, 1, 2, 3, 4, 5, 6. That -6, that -6 represents what we call the horizontal asymptote. So let me grab a couple of points real quick, and hopefully while you're looking at your calculator, you can see here I've got several values. Of course, this -8, -6, that's just because it can't round any further. It can't go quite to -6. So here's some important points to consider. -1, -5. I'm going to mark that one. I'm going to mark 0, -3, which is not only important for my graph, but also important because that's my y-intercept. Then I've got 1, 3. And that's about all that will fit on here. So let's go back to our paper and let's draw this. Remember, this thing cannot go past -6. That's the asymptote. But then it curls up through these points and it goes on off as it goes upward. So here's the answers. Remember, domain. This thing is not restricted from left to right at all. So my domain can include all values from -infinity to +infinity. However, my range, because it technically has that asymptote, like I talked about right there at -6, my range has to be from all values from -6 and up. Okay, so again, let's go ahead and go back down here, and I have that asymptote marked as orange because there is a specific question that gives you a, just like this one, an exponential function where you have to state, I think it's multiple choice actually, what the asymptote is on the test. So again, there's an additional question that has this. There's also a question where you have to answer all these. So you have to graph it, state the domain and range, the end behavior, the y-intercept, and the asymptote. So let's talk about that end behavior. Again, remember what this means. As x approaches infinity. So that means as this graph is going to the right, what's y doing? Well, it's going up. But as x is going off to the left, what's y doing? Well, it's approaching that asymptote. So it's approaching -6. And again, if you recall, we talked about the y-intercept is where it crosses the y-axis. In this problem, that's at 0, -3, which you can see we graphed it. But it's also in your table. If you look at the place where x is 0, that's your y-intercept, where x is 0. All right, so let's go on down here. Here's number 4. Again, it's another exponential graph. Here are the points and all of the information. I don't have it marked specifically because the one that's on the test looks more like the one above it that we just did together. So pause this if you need, but there's the answers for that problem. Same with number 5. There is one logarithmic graph on yours, but it looks more like number 6. So here's this graph, and here's the domain and range and end behavior, x-intercept and asymptote for this problem. So pause it if you need to, but we're going to move on down to number 6, and we're going to look at this one because it's, again, it's more like the one you're going to do on your test. So let's go graph this thing. And hopefully you all recall where to find your log base. It's alpha window number 5. And I'm going to put my 1/2, which I'm just going to do 1 divided by 2. Oops, this is 1 divided by 3, 1/3. And then inside, I'm putting my x plus 2. And then on the outside, I'm putting plus 1. So remember, this is a logarithmic graph, which does the exact opposite thing. So remember, this is where you find your asymptote here. Look, this thing shifts over 2 to the left. So your asymptote's an invisible line here that's going up and down at -2. So again, I'll mark that on the graph on my paper. It cannot go to the left of that because that's an asymptote. That's what it stands for. It's something that's like an invisible line that this graph will approach, but it'll never ever cross it. So let's go find a couple of nice points. Go to your table, and you start seeing them right down here. You see all those errors? That's the asymptote. Causes it to be an error. So we got -1, -1. I'm sorry, -1, +1. We've got our x-intercept this time at 1, 0. And let's see if we have any more nice points. There's one, 7, -1. And that's really all I need. 3 good points. So let's go back to our graph. And again, remember, my graph cannot cross that asymptote. So it's approaching these points, and then it starts curving. It goes off and through them like so. Again, remember, when you're graphing these on your real test, I expect you to have points that you're putting your line through. If you just draw some random line, you're probably not going to get full credit for that, because I expect you to graph it in your calculator, look at your table, pick some points, and enter those into your graph. Now, again, if you notice, domain here is also marked orange because there's a logarithmic question where it only asks you what your domain is. Well, remember, domain is what x can be, and since you have that vertical asymptote, it's affecting what x can be. X can be all values from -2 and to the right, so approaching positive infinity. For logarithmic functions, those are the ones where your range is unlimited, -infinity to positive infinity. Now, the end behavior, I'm going to skip for a second. X-intercept, again, that's where it's crossing the x-axis. That's right here at 1, 0. Notice the difference between it and your y-intercept that we just did with the exponential graph. The y-intercept is where x is 0. The x-intercept is where y equals 0. So make sure you understand the difference between y-intercept for exponential functions and x-intercepts for logarithmic functions. Now, your asymptote, we already said, is this invisible red line that I've actually drawn. I just did it with a dashed line. Well, that's only crossing the x-axis, so it's x equals, and it's crossing it at -2. Now, the end behavior, we kind of skipped this when we did it. When you do end behavior for logarithmic functions, you're supposed to actually reverse them. So you're supposed to say this: as y approaches infinity. So as y goes up, what is x approaching? Well, if you look up here, as y is going up, x is approaching your asymptote, which was -2. And then the other one says as y is approaching -infinity. So as this thing's going down, what is x approaching? Well, it's going to the right, so it's approaching positive infinity. So we didn't really talk about that much. I think we may have just mentioned it real quick, but again, end behavior on that is going to be probably extra credit if you get that right. So I'm not going to count off on that part on the test. But just be expecting to have one just full out graph where you have to graph it and name all those things, but then also expect a second question where you have to name the domain of a logarithmic function. So you can graph it and look and see what it doesn't cross. Okay, here's 7, 8, 11, and 12. Again, those are still good problems, but I felt like the ones that are on the test look more like the others. So you can pause it here if you'd like and just check to see if you got those right or write those down real quick. But again, on the first of each problem, I reminded you of the loop. To rewrite something from exponential form to logarithmic form, and to write something from logarithmic form to exponential form, remember, follow the loop. So let me just show you this, okay? Number 9 and 10, we're rewriting a exponent as a log. So if you look at number 9, the base of your exponent is 10. So we're going to do log base 10, and then we're following the loop. Log base 10 of what? 54 equals what? 2x. And this one doesn't want you to solve it, it just wants you to rewrite it. So there you have it, okay? Number 10, again, there's one that you can expect to be on your test that looks like this one. What's the key to this problem? Well, hopefully you notice that the base is e. Remember, when the base is e, you don't write log, you do a natural log. So you do natural log. It's understood to be base e of what? That whole thing, x minus 2. And what does that equal? It equals 6. Now, I put the x minus 2 in parentheses just to make sure, to remind you that that whole thing is together. So that's really important, actually, in this case, so don't forget that. So it's ln of x minus 2, that's your argument, that's why it's all in parentheses, equals 6. So that's rewriting from exponent to log. So now let's look at a couple where we're rewriting a log as an exponent. Remember the rule, the base of your log, that's 4, becomes the base of your exponent, and then again you do the loop. 4 to what power? X equals what? 90. So 4 to the x equals 90. And then number 14, the only difference is, remember, when you just have ln of x, there is still understood to be a base. And what is that base? Well, it's understood to be an e. So to rewrite this as an exponent, I do e to what power? The 38th equals what? X. So e to the 38th equals x. So don't forget, when you have ln, it's understood to be base e. All right, so there you have that going in both directions. Very simple problem. I wouldn't expect many of you guys to miss this. Same for all of these. Again, your instructions are very clear. It just says evaluate, and you are more than welcome to just use your calculator. Alpha, window, number 5. Alpha, window, number 5. Like I said yesterday, don't expect that if you forget where to find that you can call me to your desk and ask me where it is. We've done this enough. You should know. Okay, so let's go to the calculator, and I'm going to go back out to the home screen, and I'm going to do number 16. Alpha, window, number 5. Log base. It's log base 81 of 3. And you're going to get a fraction, or technically you got a decimal, 0.25. If you wanted, you could always change that. So second, y equals, you could always, no, not second. You can always change that to a fraction by doing alpha y equals number 4. We'll change that fraction or decimal to a fraction, so that's 1/4. So 0.25 or 1/4, either one would be 100% fine. And let's do one more, alpha window number 5. It's log base 7 of 95. And this one's not going to come out as something you can write as a fraction or decimal. So you're just going to have to round and say this one's approximately 2.34. And again, those are orange because you can expect to see two problems from this section that look very similar to this on your test. So there you have it, 16 and 20. All right, here are 17, 18, 21, and 22. I encourage you to type those in on your own. Remember number 22, you can use the button in your calculator that's just LN. But anyways, hopefully you guys can type those in without any problems in your on your own. 23, you don't have one that really looks like this on the test. Similar maybe, but not exactly. So I went ahead and solved that. If you need more time on it, please pause the video. Same for 24. Again, if you need more time, pause the video. But these are the problems where if there's log on both sides, you drop off the logs. And then you just take what's remaining and you solve it. So I did just that on 23 and 24. Let's do 25 together because there is one that looks similar to this on the test. Once again, it's log equals log. I know they're natural logs, but still, it's log equals log. So we drop them off. So we're left with p squared minus p equals 6p plus 18. So the reason I want to do this one is because you're going to have one that does this. You're going to need to load up one side. So we're going to subtract 6p from the negative p, and we're going to subtract the 18 from really nothing. And what that's going to leave me with is going to leave me with p squared minus 7p minus 18 equals 0. And we're going to factor this problem, because see how you have p squared and p? You can't just solve for p. You got to factor it into two binomials. So what is it that multiplies to get that p squared right there? Well, we've talked about that a lot. That's p times p. What multiplies to get a negative? We've said that means one of these have to be a positive and one of them has to be a negative. So what we're doing is we're looking for the two numbers that will multiply to get 18, but have a difference because the signs are opposite each other. They have a difference of 7. So if you think about that, what multiplies to get 18 but has a difference of 7? Hopefully most of you guys thought of 2 and 9. 2 times 9 is 18, and the difference between 2 and 9 is 7. So the last thing we have to decide once we realize the numbers are definitely 2 and 9, is what sign dominates when we get these two together? Negative does. So negative has to go with our bigger factor, which is 9, and the positive has to go with the smaller one, which is 2. So here's what I do with this. I take those factors, I take p plus 2, set it equal to 0, and solve. So I subtract 2, so p equals negative 2. And then I take p minus 9, I set it equal to 0, I add 9, so p equals positive 9. So those are my two solutions for this. Again, go back and check them. Negative 2 squared is 4. 4 minus negative 2 is 6. 6 times negative 2 is negative 12 plus 18 is 6. So those are right. And if you try the 9 squared, 81 minus 9 is 72. And 6 times, yeah, that's going to do it. Hang on. That's what 81 minus 9, 72. 6 times 9 is 54 plus 18. So they both actually work. So nothing is extraneous in this particular problem. All right? So there's 25, which looks a lot like a problem on the test. Be prepared for one like that. There's not one technically like number 26. Again, it's a log equals log problem. I dropped off the logs. You can look at my process there. There's not one that looks like this on the test. If you want to pause it and look at that, you can. Same for number 27. This one's not log equals log. So this is the first one on the review where we rewrote it as an exponent. So you can see what I did here. There's better ones on this review that look like the test problems. So you can pause it on this one if you would like, but I'm going to move on to 28 and look at this problem with you. Okay? This one looks a lot like one that's on the test. So the first thing we got to remember when this is a logarithmic problem like this is you've got to isolate this. You got to isolate this. So the only thing that's there that needs to move is this 5. And it's being multiplied. by that. So hopefully you guys remember, to get rid of multiplication, we divide. So if I divide by 5 on both sides, I'm going to be left with ln of the whole argument is 2a minus 1 equals 15 divided by 5 is 3. So we're ready to solve this problem because it's now isolated. So we're going to remember that this is a natural log. So the understood base here is e. So I'm going to write this as an exponent. E to what power? The third power equals what? 2a minus 1. So go to your calculator and type in second divided by and raise it to the third power. E to the third is 20.09. All right, so let's go back to our paper. We got 20.09 equals 2a minus 1. So the first thing I'm going to do is I'm going to add 1. So that's 21.09 equals 2a. Then I'm going to divide by 2. So 21.09 divided by 2 is approximately 10.545. You could round to 10.55 if you'd like. That'll be just fine with me. But here is my answer. And that is how you solve. Please expect to see one very similar to this on the test. All right, let's keep on moving. 29 and 30 are both good problems. Don't get me wrong, they're good problems. But I did not put one on the test where you had to make the bases the same. I chose not to because I just like the other way a little better, and thought you guys did a little better with those. So I took it off. But if you look at number 29 and 30, those are the ones where we created the bases to be the same. That way we could drop off the bases. Pause it there if you need to look at those. 31 is the first exponential equation that you need to write as a logarithm. So we follow that same loop. Log base 8 of 48 equals n minus 5, and then you solve. Pause it there if you like, but we're going to move over here to number 32. Now, when we did this problem, or these types of problems, remember, we focused on getting that isolated, right? That's my base of my exponent. So the first thing we need to move to get that isolated is at 11. We got to add 11. So 2 times 3 to the 4y will equal 72. Then we're going to, still not isolated, we're going to get rid of that 2 by dividing by 2. So 3 to the 4y power will equal 72 divided by 2 is 36. Now that we've got this thing isolated, we're ready to write it as a what? As a logarithm. So remember, the base of your exponent, which is 3, becomes the base of your log. So log base 3 of what? 36 equals what? 4y. So we're going to go to our calculator, and we're going to type in alpha window number 5 log base 3 of 36, and that equals about 3.26. And then I'm going to, if you look back at your, and I'll show you in a second, we're going to divide that by 4. And our answer is going to be about 0.82. About 0.82. So again, go back to your paper, and you'll see here the whole problem worked out. Again, we did the log base 3 of 36 and got 3.26, and then I divided it by 4, 0.82. So expect to see one like number 32 on your test. Okay, number 33, I did not put one like it. So if you'd like to pause and look at that problem, I wrote it as a natural log because it had base e. But I did put one a lot like number 34, which is the same thing. Look, this is the base of 2m minus 5. That is what we have to isolate. Very similar to the last problem. So first, I need to add 7. So negative 3 times e to the 2m minus 5 equals negative 34 plus 7. Again, I know you guys struggle with these sometimes, so please feel free not to forget. You can use in your calculator right here, negative 34 plus 7 if you need to. And that equals negative 27. Let me go back to my paper, okay, so you can see this. We're going to now divide by negative 3. So we have e to the 2m minus 5 equals negative 27 divided by negative 3. The negatives cancel, and our answer is just 9. So very similar to the 33 problem. Since your base is e, I'm going to rewrite this as a natural log. Well, the natural log base e, understood base e, of what? 9 equals what? 2m minus 5. So again, I'm going to go to my calculator. The natural log, that's right here, look at my cursor, that's ln of 9. So that's approximately 2. That 7 is going to round that up to 0, so it's going to be 2.2 equals 2m minus 5. I'm writing all this down. I'll go back to it in a second. The next thing we're supposed to do is add 5. So if I add 5, that's going to be 7.2 equals 2m. And then I'm going to take 7.2 and I'm going to divide it by 2. And that gives me approximately 3.6. So m equals 3.6. So let me go back to the paper so you can see all of that worked out and done. There it is. ln of 9, like we said, 2.2. I added 5, and then I divided by 2. And there you have it. That's 34. All right, let's move along. Again, there's some more problems. There's 1, 2, 3, 4, 5 that are going to be on the test. We're going to change that last problem, which I'll show you in a second. But let's look at these two first, 35, 36. Remember, there's two key things with this. One, make sure you're using the right equation. And again, you're going to be able to use your formulas to remember, formulas to know, note sheet on your test, but just make sure you're using the right equation. So this says Sophie's collection of dolls from the 19th century currently values $77,000. The value increases by 11.7 annually. 11.7% annually. Write the function and then find the value in 2025. Let's see, what? There's something missing from this. It says from the 19th century. So I don't know where the mistake was made on that, but you don't have a beginning date. So let's just say that the beginning date was 1999. All right. We're going to say that. I don't know why that was left out. Maybe I'm not seeing it. We'll say it's 1999, and we want to figure out the value in 2025. So first of all, let's write the equation. If it says that it's just increasing by 11.7% annually, that is appreciation. So that's principal times 1 plus r raised to the t. So that means that A will equal the principal amount, that's the original amount, that's $77,000. And then you're adding, because it's increasing by 11.7%. Remember, move your decimal 2 to the left, so that's 0.117, and that's raised to the t power. So that's going to be 77,000 times 1.117 to the t power. That's the equation, okay? Remember, some of these problems, they just want you to solve. Some of them, they want you to write the equation. This one's the equation. Now here's the solve. From 1995 to 2025, how many years is that? So we got 77,000 times 1.117 raised to what? Well, 2025 minus 1999 is 26 years. So we're going to raise this thing to the 26th power. So let's go type that in over here on our calculator. So we have 77, I'm going to clear all this out. We got 77,000 times 1.117 raised to the 26. I think this is going to be a crazy amount. This thing is going to be worth, and this is probably a little absurd, it's going to be worth $1,367,329.63. I don't know. Maybe that's possible. Maybe I should start collecting dolls. But anyways, that's a crazy amount. So this one had two answers. It had the equation and it had the answer after 26 years. Okay? 36. A baseball card was valued at $200 in 1980 and it's increased by 7% each year. Write a function to model this. And then, so this one's very similar to the last one. I mean, extremely similar. It's just appreciation. So it's principal times 1 plus r raised to the t power. So here we go. Here's the equation. The principal amount was $200. We are adding, because it's going up, it's increasing by 7%. That's just 0.07 raised to the t. So my equation is 200 times 1.07 raised to the t power. Okay, so that's part one. The next part, though, is let's solve. Okay, well, we're talking about from 1980 to 2020. How many years is that? That's 40 years. So I'm going to type in 200 times 1.07 raised to the 40th power. That's huge. That's a bunch of years. So let's see how much it increased over those years. 200 was the starting amount. It increased at 1.07 raised to the 40th power. So by 40 years, it's going to increase all the way up to $2,994.89. That'd be pretty good. Just take a long time to do that. So there you have it. All right. Let's keep cruising. 37. Miles invested $2,400 into a retirement account that earns 1.8% compounded monthly. Okay, this is compound interest because it says that. So that is P times 1 plus R over N raised to the NT power. And since it says compounded monthly, what does that mean, monthly? It means N equals 12. So here's my equation. It says write a function and then tell what it'll be after 25 years. So my equation is 2,400 times 1 plus R is 1.8%. That's 0.018 over 12 because monthly raised to the 12t. So let's go over here and type this in and see what this looks like. 1 plus alpha y equals, number 1, we got 0.018 over 12. And let's see, yeah, that's a great percent. So we're going to rewrite this as A equals 2,400 times 1.0015 raised to the 12t. Let me go back to my paper and show you that. Here's the equation. Really nice equation because that worked out. We didn't have to round. It's perfect. They want to know now, what's the balance going to be after 25 years? So go type in a calculator 2,400 times 1.0015 raised to the 12 times 25 power. All right, so let's go try it. 2,400 times 1.0015, and that's raised to the 12 times 25 power. So boom, there it is. Looks like it's going to be approximately $3,762.68. And there it is. That's the amount. All right. If you look at number 38, this one is very similar. It's just compounded quarterly. Let me go back. It's compounded quarterly. So there you can see it's done very similar. But again, there's only one of those on the test, so I just wanted to go ahead and do one. Number 39 and 40. 39 is a doubles, and number 40 is a triples 3 times. I did not put one of those on the test. No big deal, really. I just decided not to. Number 39, it wanted to figure out how much it'll be after 8 days. Number 40 just wanted you to write the equation, but I just left that off the test. Okay, so 41. Pause those if you need to. You invest $150 into an account with 2.5% annual interest compounded continuously. See, that's a key. How long will it take for your money to double? So this is actually finding time that we did just yesterday, or Monday, I should say. So we know that it's this formula, A equals PE to the RT. So first of all, the 150, that's my principal amount. Okay, that's what I started with. E is what we call a mathematical constant. Your R value is 2.5%, that's 0.025. And it asked me how long, T, is it going to take for that money to double? What is double 150 bucks? It's 300. So that is my A value. 300 equals 150 E to the 0.025 T. So like we did yesterday, remember, we've got to isolate that E to the 0.025 T. So we're going to first divide by 150. 300 divided by 150 is 2. And then I'm going to rearrange this. I'm going to put the E to the 0.025 T on the left, and that equals 2, just so we can follow that loop. And again, because this is a base E, I'm going to use natural log of what? 2 equals what? 0.025 T. So the last move I'm going to make is to divide by 0.025. So let's go to our calculator and let's do that. Let's type in ln of 2. Don't forget to close that parenthesis off. That way it finalizes that ln of 2, and then it will divide it by 0.025. And that equals about 27 point, what is that, 72, or no, 73. So 27.73. And the question said, it's in years, compounded continuously, so that's going to be 27.73 years. Not very good, right? To go from 150 to 300. Bad percentage. So anyhow, number 42 is very similar. Number 43, you can omit it. It was one of those monthly problems that we skipped. And 44 was also a monthly problem that we skipped. But I want you to mark off that last little statement, and I want you to change it, the last statement, to this. Create an equation that represents this, then find the value of the machinery after 6 years. I wanted to do one that was depreciation, but I didn't want to do it monthly. I wanted to just straight up do depreciation. So remember, that's this formula. A equals P times 1 minus R to the T power. So here's my equation. A will equal P, that's 45,300, times 1 minus my rate. Well, that's 9.1%. So that's 0.091 raised to T. So if we simplify that, here's the equation. 45,300. And if you go to your calculator, 1 minus 0.091 is 0.909. So if you write it in simplified form, the equation would be 45,300 times 0.909 raised to the T. So then it says, hey, find how much it'll be after 6 years. So 45,300 times 0.909 raised to the 6th power. So let's go type that into the calculator, and let's see. We got 45,300 times 0.909 raised to the 6th power. So it's going to drop all the way down to $25,555.80. 33 cents in 6 years. So let's go back to the paper and finish this thing up. This would be the 2 answers that they would expect on the test. So if you go back and you count the orange, you will see 20 questions. That's because the test has, guess how many? 20 questions. So if you look and focus on those 20 that are highlighted in orange, then you will be prepared and ready for your test, whether it's Wednesday or whether it's Thursday, just depending on when you'll be in class because of the ACT. So please study this, be prepared, and if you do, I think you will be pleasantly surprised with how you do on the test. Anyways, hope you have an awesome day, and good luck on your test.